Orchard, himself creative. Jeff Orchard's wickedly awesome research on medical and forensic image processing. Looking very much forward to you, Jeff.
Is this on? Yeah, okay. I'm running out of titles for my talks, my research overview talks, so today I'm talking about the wickedly awesome research on medical and forensic image processing. So I gave a talk before, but I've added the wickedly awesome part. Actually, I've also added the forensic part. It's kind of new to me. It's sort of an area I'm going into. So there's just a little bit of that. So overview of my talk, I'm going to give this overview, and then I'm going to give the rest of the talk. Okay, so now on to the rest. That ate up about 10 seconds. So mostly what I do is image registration. So here's an example of a registration problem that I try to solve. This is the visible human. This is a photograph of the guts. And this is a T1 weighted MR image. And you can see I've got a region of interest here. So the question is, how do I shift this to align it properly inside this area? And here's a representation of the solution that that my program has given. And you can see I'm remapping the gray levels, the contrast and brightness of the photo to try to match the T1 weighted MRI. So this is actually the anatomical photo thing inside here. Another example on satellite imagery. This is actually an aerial photo, and this is some sort of height map using some other technology. And again, I can fit it in here, and the method tries to adjust the gray level intensity. So this is all done using frequency. We're using fast Fourier transform. So the objective is speed, speed, speed. Another thing I'm getting into, multimodality. That was kind of multimodal before, but also different sort of registration method. Here's, I guess I shouldn't go too much into detail, but when you're comparing two images, one thing you can do is create a scatter plot of the pixel intensities. And you're trying to basically uncluster them. So the more tightly, you're trying to cluster them. The more tightly clustered these points are, the better registration you have. And that's sort of similar to what Ed Burskay's student was doing, except using a different cost measure. So I've just thrown some regressor lines on there, and they move around to try to fit the data, and as they move, I'm moving the images as well, which moves the points. So everything's kind of shifting around, but it seems to settle down quite nicely. So that's a registration method I'm working on. Motion tracking for MRI, as promised by Ed Burskay. I think you alluded to that in your questions. So I have a PhD student stationed at Sunnybrook Hospital working with Dr. Simon Graham. And they have motion tracking devices. Okay, first of all, an MRI, if the person moves, you get these yucky artifacts. And so we don't want, well, typically you don't want the person to move. Then they came up with programs that could try to compensate for it, but they don't do it perfectly. There's a fundamental loss of information when the patient moves. So the next step. No, this is an image I ripped off of the internet. So let's put a motion tracking camera system in there and let the person move, but track it. And as they move, we adjust the scan sequence so that the acquisition is stationary with respect to the person's anatomy. So this is mostly done by Simon Graham, but my PhD student is working on a project in there. This is the forensic part of my talk. Maya Omanovich is my master's student, and she's interested in dentistry, or odontology, she calls it. So here's the idea. We want identification using dental x-ray. So at the very top, that might be an x-ray that we could get from a deceased. Maybe they were in a fire, and there's some difficulty in identifying them. So the idea is take an x-ray and try to match it using some registration method, or actually try to register it with every dental x-ray you've got, and whichever gives the best registration, that may identify the person. So here I've shown some numbers. Each number represents basically represents the error when trying to match that image at the top with that image. So came up with an error value of 2, whatever that means. Smaller errors, this one over here, 0.39. So this is a correct match. You can see the little thing coming out of the, well, whatever that is, a filling of some sort. There's another correct match here somewhere. 1.77 up there. So we're working on that. And this is pretty early stuff, but she's staying to do her PhD, so maybe we'll go further. My other master's student, Alexei Ramatar, is working on CT reconstruction methods. So typically CT, in fact, I think all CT scanners are, everything's nice geometry. You go into a hospital, and everything's in a circle. And they're very efficient reconstruction methods because they take advantage of the geometry. But there seems to be some technology coming out where you can interweave X-ray emitters and detectors in fabric. So we're working on a method, so let's say you have this fabric you wrap around a person's leg. We can still read all this information out, read all these line integrals, if you want to call them, these like miniature X-rays. And even though everything's not circular, we still have an efficient reconstruction method. So the idea is that an ambulance driver can operate a CT scanner in the middle of the road where you happen to be laying. Wow, that was quick. I need to do more research, fill up more time.
Well, definitely wickedly awesome. There's no question about it. Questions, comments? I have one. I know that at Grand River they're looking at some new imaging technologies related to radiotherapy, where the imaging technology is mixed in the therapeutic instrument. Can you, presumably, in order to do the tracking, you need fairly good images, and I guess originally they called them portal images, were not good quality. What's happening in regard to that?
So you might be referring to other projects that I had proposed. I've abandoned that line of work. The idea was motion tracking for radiotherapy. So the tumor moves around, and you might use imaging to follow the tumor or some sort of motion tracking thing. I don't feel that's going to pan out.
Oh, okay.
So I'm not doing that.
Okay. Any other questions? David, any comments?
Well, there's some registration seems to be going pretty far now, mainly with guided biopsies, where you are trying to superimpose an ultrasound image to an MR CT image to recreate mainly radiotherapy that are interested in that. So I don't know.
Yeah, so that's an imaging. What I was talking about was the project I was working on before was monitoring external motion, so of the belly, and from that trying to derive where the tumor is. And I don't think that's that didn't seem like an approach that I could pull off. Maybe someone else can, but you were talking about portal images, so that's a possibility. So that
yeah.
if you have an imaging modality in there with you, then you're not trying to make this connection between external motion and where the tumor is. So that's more direct.
Okay.
What mathematical models do you think underlie this? Like, it seems, do you use the same models you had your PhD thesis? Like, I'm just wondering, it seems these can be unified somehow with a lot of these problems.
I like the Fourier transform.
Yeah.
I like cost functions, registration cost functions.
So energy-based methods.
And energy or intensity-based registration methods.
Any final comments? If not, thank you very much.
Thank you.